Welcome to this presentation on parasitic extraction with Hyperlinks AMS. Hyperlinks is an integrated family of products for high-speed system design, automated optimization, and verification. By design, we mean all the planning and analysis that you do before layout to define the rules you want to use to place and route the board. By optimization, we mean using automated tools to improve design performance for a metric of interest. You can certainly use an interactive design, capture, analyze, review loop to improve your design, but that takes too long. We'll look at how hyperlinks can help you improve design performance automatically. By verification, we mean post-layout analysis, or what you do once a board is routed to determine that the design is ready to release to fabrication. There are three main design application areas for hyperlinks: DDR interface design and verification, serial link design and verification, and general-purpose signal and power integrity, which overlap with some of the capabilities we'll discuss here. Hyperlinks products include Hyperlink schematic analysis, which automates parametric checks, eliminating the necessity to manually review complex schematics. Hyperlinks AMS, a powerful circuit simulator for analyzing complex analog and mixed signal designs. Hyperlinks DRC, which provides fast, rules-based design checking of PCB layouts. Hyperlinks DRC can identify layout issues in a fraction of the time that simulation requires. Screening designs with DRC before investing in detailed modeling and simulation will help speed your design cycle. Hyperlinks Advanced Solvers, which provide accurate 3D electromagnetic modeling of PCB structures and are seamlessly integrated with Hyperlinks SI and PI to provide complete front-to-back analysis flows. Hyperlinks SI and PI, which share a common user interface. Hyperlinks SI performs signal integrity analysis of DDR interfaces, SerDes-based serial channels, and general-purpose high-speed design. Hyperlinks PI performs DC and AC analysis of PCB power delivery networks, or PDNs. Hyperlinks is tightly integrated with Siemens' family of PCB design capture and layout tools. Design is an iterative process. As you lay out a board, using analysis during the physical design cycle can help you tune and improve the design in real time rather than waiting until layout is complete when it's too late to make substantive changes. Combining hyperlinks with Siemens design capture and layout can significantly reduce your design cycle and improve your design's performance. In addition to offering superior integration with Siemens PCB tools, Hyperlinks is also the most widely interfaced power and signal integrity tool on the planet. With Hyperlinks, you'll have the widest range of PCB import capabilities available. Hyperlinks AMS is the tool that bridges PCB design with simulation and analysis. It is an integrated simulation environment for analog and mixed signal design. Hyperlinks AMS is tightly integrated with the PCB design environment through Expedition Designer. It drives circuit simulation from the system schematic used for PCB layout and does not require a separate simulation schematic as with some other environments. This reduces the risk of errors and speeds the design process. Hyperlinks AMS provides multi-language modeling support including SPICE, VHDL AMS, and C and C++, with an extensive library of SPICE and VHDL AMS simulation models for AMS circuit design. It's capable of a versatile range of analyses, including standard time and frequency analyses to verify nominal functional performance, as well as advanced parametric analyses and parasitic extraction to verify performance in non-ideal conditions. The Hyperlinks AMS flow consists of the following stages. In the creation stage, we design a flat or hierarchical schematic using Designer. In the simulation stage, we simulate the design according to the components, VHDL AMS, and SPICE models inside it. We can also simulate a pre-existing schematic or PCB design after performing schematic mapping. Time domain and frequency domain simulations are typical for all designs. In the analysis stage, we can perform a variety of different analyses including sweep, sensitivity, Monte Carlo, and worst case. The analyzed data is loaded into the waveform analyzer to view and measure performances, tolerances, and variations. If we need a model that is not available in the library or a custom one, we can create other models using sources like VHDL AMS, SPICE, or from a schematic. A typical AMS flow goes create, simulate, analyze, but if new models are needed, then we model first and then create, simulate, analyze. The AMS environment has 5 basic elements. First, the simulator core. It's at the heart of the AMS environment. The simulator core accepts mixed signal and multi-domain models like electrical and mechanical models. These models can be written in VHDL AMS or SPICE. Second, model creation. AMS supports different methods of model creation, such as the model and symbol wizard, hand coding, and code generation. Third, model libraries. In addition to custom model libraries, Hyperlinks AMS comes with large libraries of VHDL AMS and SPICE models, which cover multiple technologies including analog electronics, digital electronics, mechanical, magnetic, and thermal systems, and more. Each model is represented by a symbol in the AMS symbol library. Fourth, graphical design. The system is graphically represented in the powerful design capture tool, Designer. The design hierarchy and model libraries can be easily navigated from the Project Navigator. Fifth, data analysis. When simulation is complete, results are automatically located in the Waveform Analyzer where they can be viewed, measured, and transformed in order to get a detailed picture of the design performance. Hyperlinks AMS features support for multi-language modeling with extensive model libraries included. SPICE is a popular type of electronic device model, and the Hyperlinks AMS installation includes a large library of ready-to-use SPICE models. If we want to use a model that is not in the Hyperlinks AMS install, whether in SPICE or PSPICE format, we can import the model into the project, add a symbol, and use it in a design, then set up and run a simulation. Getting from a PSPICE or SPICE format model to simulation results is a straightforward process with a PSPICE to AMS library converter tool included in Hyperlinks AMS. VHDL AMS is an IEEE standard language for modeling analog, mixed signal, and mixed technology devices and systems. Along with SPICE modeling, the Hyperlinks AMS tools support the power and flexibility of the VHDL AMS language. VHDL AMS supports analog and event-driven behavior for modeling and analyzing analog, digital, and mixed signal designs, and can go beyond the electrical domain into other design technologies. Even though VHDL AMS is a powerful language, it is sometimes easier to model behavior in a different language like C. While the Hyperlinks AMS simulator cannot directly use models written in C, you can use C-based functions and procedures inside a VHDL AMS model. Component manufacturers develop IBIS models so designers can include the analog effects of digital components in a design simulation without the manufacturer releasing important component IP. IBIS models can be added to design simulations in the AMS environment. Hyperlinks provides multiple methods and tools for creating models, which we will cover in the following slides. If you have a part in your design that does not have a simulation model associated with it, you can use the Model and Symbol Wizard to make this assignment. Every electronics design company has legacy schematics that need updating to meet the new requirements of revisions, but have no simulation data. Setting up legacy schematics for simulation requires linking simulation models to schematic symbols. The Model and Symbol Wizard is an intuitive setup wizard that guides the user step by step through the process of finding, creating, and mapping simulation models and symbols and ports, allowing even the most complex designs to be quickly prepared for simulation. The tool assists the user to select the model type and data source for the model, choose the schematic symbol, map symbol pins to model ports, map symbol properties to model parameters, add an IBIS stimulus signal to a symbol pin, and save the model and symbol to the current project or shared library. Several different model types and data sources are supported by the wizard: SPICE, VHDL AMS, Schematic, S-Parameter, IBIS, and Datasheet. Hyperlinks AMS includes a variety of tools that allow for models to be generated easily and efficiently. The Datasheet model builder is a Hyperlinks AMS tool that lets you configure an existing VHDL AMS model using datasheet parameters and save it as a new model. This tool consists of a graphical interface patterned after a device datasheet. Using a datasheet layout for common electrical devices simplifies the process of creating models and reduces the effort of writing a new model from scratch. The datasheet model builder includes several device types. Each device type includes a default model that you can use as a starting point. Use the default model parameter set to create a new model or change one or more parameters to match those in a device datasheet. After you create a model, you can use its parameter set as a starting point to create another model. The Datasheet Curve Modeler is a Hyperlinks AMS tool that enables you to automatically create simulation models that match curves given in component datasheets. In addition, custom freeform curves can also be captured and used as a source stimulus. This is done by simply pointing and clicking the pointer over a canvas that captures and stores data points corresponding to the pointer location. A model that reads in this data is generated along with a corresponding symbol. The symbol can then be placed and used in an AMS design. The VHDL model generation tool provides an easy way to create and edit VHDL AMS models. This form-based tool leads you through the various steps for creating a VHDL model and its corresponding symbol in a current project. A VHDL AMS model is automatically generated and correctly formatted with entity and architecture. This tool requires a level of familiarity with the VHDL AMS language, and it significantly reduces the chance of errors compared to hand coding. Once our design is complete with models and parts placed, we are ready to simulate and analyze. There are various types of analyses in AMS. Typical analyses include operating point, time domain, and frequency domain. In time domain simulation, AMS calculates the behavior of all models at various times throughout the duration of the analysis. For frequency domain simulation, AMS analyzes the design by applying small signal AC behavior from stimulus models in the design that provide magnitude and phase. A parametric sweep runs a complete simulation analysis using a different value of any model parameter for each analysis. This allows us to observe how the behavior of the design changes as we incrementally vary the parameter. A sensitivity analysis determines which design parameters most influence a selected performance metric. Monte Carlo analysis is a set of repeated simulation runs where user-specified parameter values of models in the design vary randomly with each run. Worst-case analysis runs 3 simulations, one each of the parameter sets that illustrate the worst-case upper and lower bounds, and one for the nominal parameter sets. Typical simulations include time domain and frequency domain simulations. In Hyperlinks, simulations can be set up easily in the simulation control dialog. For a time domain simulation, we can define the duration and interval at which each calculation is performed by defining a start time, end time, and time step control. We can also perform a fast Fourier transform on analog waveforms. Finally, we can set parameter settings affecting performance, namely convergence, accuracy, and speed, of DC operating point and time domain simulations. For a frequency domain simulation, Hyperlinks AMS calculates the behavior of all models in the design at certain frequencies. We can specify the highest and lowest frequency at which Hyperlinks evaluates the small signal behavior of the design, define the number of frequency steps per variation, and define the type of interval partitioning the frequency points, decade, octave, or linear. In addition to small signal analysis on a design, we can perform noise analysis using SPICE voltage or current sources to model design noise sources. A multi-run parametric sweep runs a complete simulation analysis, either time domain or frequency domain, using a different value of any model parameter for each analysis. Parametric sweeps are useful for automatically varying specific circuit parameters and running simulations. Currently, Hyperlinks AMS supports parameter value sweeping on a schematic when the design is netlisted in SPICE, which is the default setting. From simulation control, we can select which parameter we wish to sweep. Then we can select which type of sweep will be performed: increment, linear, decade, octave, or list. Depending on the sweep type selected, we can then define a sweep start, sweep end, and define the values included in the sweep by specifying a step size, specifying a number of steps, or typing a comma delimited list. Once simulations have been run for all parameter values, Hyperlinks AMS launches the waveform analyzer, and we can observe changes in the behavior of the simulated signals as the selected parameter is varied. The results displayed here show how the time domain position of a motor-driven load changes as we vary the motor winding resistance. A sensitivity analysis determines which design parameters most influence a selected performance metric. The Hyperlinks AMS environment supports 3 sensitivity analysis types: relative, tolerance-based, and statistical. Sensitivity analysis is used to automatically vary each component parameter or selected parameters in a design to a user-specified percentage of nominal value. Parameter values are changed one at a time so that the sensitivity of a design performance measure to each of the various parameters can be determined. Like parametric sweeps, sensitivity analysis is run in combination with one of the main analysis types, time or frequency domain, and the controls are built into the multi-run tab of the simulation control dialog. The user can select which parameters to analyze and specify how much those parameters are perturbed. The images on this slide show the results of a sensitivity analysis performed on an H-bridge motor driver circuit. 7 parameters were analyzed, and based on the results displayed in the bar graph, the motor damping coefficient D is the parameter that most influences the position of the driven load. Sensitivity analysis is often used to determine the appropriate nominal design parameters early in the design phase. Parameter tolerances are often not known until later in the design, but sensitivity analysis can still measure design performance based on changing nominal parameters. Monte Carlo analysis is a statistical analysis method that randomly varies model parameters within a specified tolerance range and distribution. Monte Carlo analysis is often used to help determine the manufacturability of a design, that is, given the specified tolerances, how robust the design is when manufactured in large quantities. Since component parameter tolerances are required for Monte Carlo analysis, it will often be performed a little later in the design process when these values have been established or guessed. Of course, these tolerance values are likely to be changed as a result of running the analysis after learning the effects they are having on the design. Using Hyperlinks AMS's powerful post-processing capabilities, it is also possible to perform correlation studies and determine sensitivities of performance criteria to device parameters. Armed with this information, you can make an informed decision for system optimization, for example, cost versus performance. The ability to do this for systems containing a mix of technologies with a combination of SPICE and VHDL AMS models makes Hyperlinks AMS a very powerful tool for virtual, mixed technology system integration. Worst-case analysis helps to determine the minimum and maximum range of measurement variation as a function of parameter changes. Worst-case analysis results are determined as follows. The results of a previously run sensitivity analysis are used to establish the sign relationship between each parameter and the measurement of interest. For example, if the resistance of resistor R1 increases, does the measurement increase or decrease? This effectively determines the sign of the slope between the parameter and the effect on its given measurement. The worst-case analysis determines this relationship for each parameter in a design that has a distribution specified for it. It ignores all other parameters, even if they were used in the sensitivity analysis. The result is that Hyperlinks AMS performs 2 simulation runs, one for all the parameters set to the limit of their distribution resulting in a measurement increase, and one for all the parameters set to the limit of their distribution resulting in a measurement decrease. These are the worst-case limits for that particular design. An optional nominal simulation can also be performed to view along with the worst-case analysis waveform envelope. The highly versatile Hyperlinks AMS waveform analyzer provides a dynamic graphical display of data produced by mixed-signal simulation. Use the waveform analyzer to observe and investigate signal transitions, what-if analyses, timing and delay effects, or other areas of interest. We can zoom analog, digital, and mixed signal displays to user-specified magnification levels, scroll along the horizontal axis, and measure between points on a waveform using cursors. We can drag and drop waveforms into the graph window. We can also overlay waveforms for comparison or display multiple separate graphs. The measurement tool allows us to perform an enormous range of measurements depending on the analysis type. This includes, but is not nearly limited to, rise time, fall time, overshoot, and period for time domain analyses, bandpass, high pass, low pass, gain margin, and phase margin for frequency analyses, and statistical measurements such as maximum, minimum, mean, median, range, and best fit lines. Other tools featured in the Waveform Analyzer include the Waveform Calculator, which performs post-processing calculations on Hyperlink's AMS waveforms for advanced analysis or debugging, and the eye diagram tool to generate eye diagrams by dividing the source waveform into segments using triggers. Let's move on to the topic of parasitic extraction in Hyperlink's AMS. Any physical circuit in the real world will suffer from some degree of parasitic effects. This includes parasitic capacitances, inductances, and resistances. Board-level parasitics can negatively affect circuit performance. While their values may be small, their cumulative effect on design performance can be significant. For instance, trace parasitics can affect the characteristics of analog filters. In digital signals, parasitics can degrade rise and fall times, induce ringing, and cause bit errors. Noise coupled from digital signals can negatively affect the behavior of a sensitive analog signal. In power electronic boards, parasitics can cause unintended switching in nearby logic circuits. Correctly accounting for these effects in simulation requires an accurate model of board traces and their collective behavior. As design frequencies have pushed higher and higher and integration has increased, layout parasitics have become an important consideration in analog and mixed signal design. Hyperlink's AMS and Hyperlink's advanced solvers have been integrated to offer a unique, powerful, and versatile solution for evaluating the effects of interconnect parasitics in analog and mixed signal designs. The Hyperlink's advanced solvers are a set of 3D electromagnetic field solvers within the Hyperlink's product family of PCB design verification tools. There are 3 different solvers that can be used for extracting board layout parasitics and creating parasitic models. The design process starts with system schematic capture and AMS simulation in Hyperlink's AMS. Once the design meets its functional specification, the printed circuit board is then laid out in a physical layout tool. Parasitic extraction is invoked directly from the Expedition schematic editor and uses one of the 3 Hyperlink's advanced solvers, chosen based on design bandwidth and design analysis, to generate the parasitic model. Hyperlink's AMS then back-annotates this parasitic model into the simulation netlist to analyze how the board layout affects design performance. When the simulation is complete, results are viewed, measured, and compared with functional non-parasitic simulations. Electromagnetic field solvers are the most accurate way to simulate the behavior of circuits and signals by directly solving for Maxwell's equations. As mentioned before, Hyperlink's advanced solvers features a selection of 3 solvers, and in Hyperlink's AMS, we select which one to use in parasitic extraction based on the desired simulation speed, accuracy, and type of analysis. The full-wave solver is a powerful 3D, broadband, full-wave electromagnetic solver based on proprietary accelerated boundary element technology. It solves Maxwell's equations over a wide bandwidth called from DC to daylight. It creates a model in scattering parameter format and is accurate well into the gigahertz frequency range. The fast 3D solver features an accelerated full 3D electromagnetic quasi-static extractor that rapidly extracts SPICE subcircuit models. It is ideal for lower frequency applications where capacitance and noise coupling are the primary concern. Finally, the hybrid solver assumes transverse electromagnetic mode or TEM propagation on traces and combines 3D and 2D analysis for faster solve times. It is well suited for regular transmission lines and plane-to-trace coupling. Let's observe the basic steps of a parasitic analysis. The full, detailed, interactive workshop can be found on the Siemens Xcelerator Academy in the Explore Hyperlinks on-demand training. The workshop consists of an example design for a power supply board, shown here. We will start by obtaining a nominal simulation of the design by toggling parasitics off in the netlist. Then we set up and perform a time domain simulation using simulation control. The simulation results appear in the waveform analyzer with the nominal non-parasitic waveforms. We are interested in two waveforms, A-out and FB or feedback. We note that A-out is a digital signal with rising and falling edges, while feedback is an analog signal. Now we will perform parasitic extraction, which is set up in the Extract Parasitics dialog. Here, we select the nets of interest for parasitic extraction, select the layout file corresponding with our physical design, choose which 3D field solver is most suitable for our analysis, define the frequency range and reference net, and choose whether to run Hyperlinks Advanced Solvers in an integrated mode or to launch it separately. Once parasitic extraction is complete, we return to simulation control and rerun the simulation with parasitics included. The results appear in the waveform analyzer, and we can overlay them with the previously obtained ideal non-parasitic waveforms for comparison. We note that A-out experiences ringing on rising and falling edges, a result of parasitic capacitances. However, feedback also experiences ringing at the same time despite having no edges. The reason is clear when examining the layout. A-out and feedback are very close together and are in parallel, creating parasitic capacitance between them. We update the board by moving the two traces to the opposite side of the board, extract parasitics again, and resimulate. The ringing on feedback is drastically improved. Try this yourself and observe the full results in the Hyperlinks AMS Parasitic Extraction Workshop on Siemens Xcelerator Academy. We can see that Hyperlinks AMS, with Hyperlinks Advanced Solvers integration, is an efficient and accurate tool for performing parasitic extraction. It allows us to anticipate parasitic effects during the simulation phase rather than after board fabrication, greatly reducing the time and money spent on a design. Hyperlinks workshops get you up and running quickly by documenting complete workflows with detailed step-by-step instructions and videos. Hyperlinks workshops guide you through the process with working examples so that you can hit the ground running on your own design simulations. Hyperlinks workshops can be downloaded from the Support Center by accessing the knowledge base article named Workshops for Analyzing High-Speed PCB Designs. You can see a list of the different workshops on the right of this screen. And that's it for this presentation. Thank you for your time and attention, and remember, it's easier with hyperlinks.